Hi, Thomas.
Hello.
How are you this evening?
I'm good. How are you?
Good. All right, what are we going to do tonight?
All right. So tomorrow I have a test on um, basically everything we've been covering for the last like week or two. So I'll just post or I'll just chat something to you.
Okay.
Basically, that's what the test is on.
Direct and inverse, fundamental theorem of variation, graphs of these models, and creating models for these data.
Yeah. So I mean, if we could just go over it. I mean, I feel like I get a lot of it. The graphs are probably some that I have trouble with, but
Okay. Let's talk about direct.
okay.
What's that formula?
It's y equals x, or k times x.
Okay. And inverse?
Inverse is y equals k over x.
Okay. So let's talk about direct again. If when y equals 3, x equals 6, what is y when x equals 10?
Let's see. So y is 3. Well, it's just 10 divided by 3, isn't it?
Not quite. In other words, the secret to this is solving for k
Right.
based on these two numbers. So substitute 3 for y, 6 for x, and solve for k. What do you get?
Right. You get 3/6, or I guess half.
So k is equal to 1/2. That
Right.
means the formula, the specific formula, is this. It's no longer y equal kx, it's y equals 1/2 x. So now when I give you a new x, what is y equal to when x is equal to 10?
Oh, right. It's 10 times half, or 1/2.
Exactly. 5. Okay, so that's
Yep.
essentially everything you need to know about direct except the graphical. Let's graph this. Y equal 1/2 x. What's the first thing we notice? How would you graph that?
Um, I always have trouble with this. It will,
Okay, think of
yeah,
the y equal mx plus b.
right. So the 1/2 is the slope, isn't it?
Correct. What is b?
B is the y-intercept.
Right. Which in this case, what is it?
Uh, we don't know.
It's 0.
Oh, okay.
Okay, so we know the first thing about this graph is it goes through the origin. And then it has a slope of 1/2, which is approximately like that.
Okay.
So the graph of direct relationships is linear. Not
Right.
only
And it
is
always
it,
goes through the origin.
yeah, not only is it linear, but it always goes through the origin. Because if it didn't, let's say it was like this, well then y would be equal to 1/2 x plus 3. And we don't have this plus 3 in our direct relationship. So
Right.
the graphs have to go through the origin and they have to be a straight line.
Okay.
As I indicated last time in our session, I'm a little confused by the graphs of these. Because in this case, y is directly proportional to x. But what if y was directly proportional to x squared? Then that's the way that would unfold. And that graph is not linear. That graph is some form of a parabola. So I'm not quite sure how to answer your graphic. It kind of depends on what they've taught you in class. Have they given you this type of problem, or has everything they've given you been linear?
No, they've given that type of problem.
Well, then I don't know what one can say about the graph, because since it can be directly proportional to x, or it can be directly proportional to x squared, or the square root of x, the graph might look like a lot of things. It could be linear, it could be quadratic, it could be cubic. So I'm not quite sure how to answer the graphic problem. Assuming that it's linear, in other words, assuming it's this nature here, then you could say that it's always a straight line through the origin. But a lot of direct relationships are not linear. You can have y be directly proportional to x squared, or even the square root of x. So it doesn't always have to be precisely this. And let's do an inverse. Where y equals k over x. And again, that's not linear. It's hyperbolic. But again, this could be x squared. So let me give you one here. When x equals 2, y equals 6. So when x equals 10, what does y equal?
Well, it's the same as before. You just plug it in and try and find k. So,
Right.
y equals, or I mean 6 equals k over 2. So k equals 12.
Okay. So our equation now becomes this. In other words, this is called the general, this is called the specific. The specific equation would apply to our model, whatever it is we're modeling. You can have a lot of direct or inverse relationships where k is different. So what is y when x is 10?
It's 12/10.
Okay. That is the most likely kind of problem you're going to be faced with, is those two.
Yeah, sometimes it throws me off because, for instance, I have a packet here. It says the number of square tiles it takes to cover a floor varies inversely as the square of the length of a side of a tile. So sometimes I forget to add that, those little, or it'll be the cube or, you know.
Okay.
But yeah, I kind of figured that out.
Let's do that problem that you just had.
Okay.
Does it give you a y and an x and then asks you for a new y and an x?
Yeah, so basically it says
Do it.
the number of square tiles it takes to cover a floor varies inversely as the square of the length of a side of a tile. If it
Okay.
takes 140 12-inch tiles to cover a kitchen floor, how many 6-inch tiles will it take?
So x is what when y is 140?
So
Meant to say tile.
x is 12.
Right. 12 inches. Did the original premise say anything about in feet or inches or anything?
No, or yeah, inches, sorry.
It is in inches. Okay.
Yeah.
So let's solve for, what's the next step?
So the next step would be to find k,
Okay.
and you would multiply 12 on both sides.
Well, let's lay out the equation first.
Okay, 140 equals k over 12.
Over 12 squared.
12 squared.
Remember, it's inversely proportional to the square of the side of a tile. And the tiles are 12 inches on a side. Is that correct?
Yeah.
Okay, so K is equal to 140 times 144. Do you have a calculator?
Yeah. One 20,160.
So that's K. And here is our specific formula. So now what's the question they're going to ask?
So now it's
Oh, 6-inch tiles. What is,
yeah, 6
how many tiles are needed? Okay, so right?
Yep.
What's that answer?
So that would be 560.
4 times as much. Well, does that make sense? It does. Notice that there's our floor. And if we're going to cover it with 12-inch tiles, it's going to look like that. We need 140 of them.
Mm-hmm.
Well, if we make these 6-inch tiles instead, notice that I need 4 6-inch tiles to cover one 12-inch tile.
Right.
So the total number of 6-inch tiles that I need to cover the same floor should be 4 times as much. And it is.
I feel like someone could just figure that out by looking at the problem.
They could. You could use straight geometry here. You
Yeah.
wouldn't have to use this inverse relationship. But it's a good example of an inverse relationship.
Yeah. Let's see. Oh yeah, I always have trouble with these. Here's a problem. It is, suppose in a variation problem, the value of x is quadrupled. How is the value of y changed if y varies directly to x cubed?
Okay, so this is how we would set y varies directly with x cubed.
Mm-hmm.
And the question was, what happens to y when x is what?
Quadrupled.
Quadrupled, okay, by a factor of 4. So x becomes 4x. Well, k isn't going to change, so what's going to happen to y? In other words, if this was just that, and y went up by a factor of 4, if x went up by a factor of 4, y would go up by a factor of 4, right?
Right.
If it was x squared and y or x went up by a factor of 4, what would happen to y?
I don't know. I get confused because I always think it would just be the same,
It
but
would go up by 16. Because what we would essentially do is k doesn't change, and instead of x, I'm going to put 4x. And it was cubed, right?
mm-hmm.
That was the problem. Okay, so now what happens when you put 4x in place of x and you cube it? The new equation is so y actually goes up by a factor of 64.
Okay. So basically you just plug it in and
Yeah.
and
Yeah,
that's
because
the answer.
in other words, they don't give you a y and an x, so you can't solve for k. But we can plug in 4x in place of x, and then that whole thing has to be cubed.
Right. Okay.
Now, the problems that used to give me trouble were where I would have a table, or they would give me a table, and they would say, tell me if this is a direct, inverse, or neither relationship. Have you had problems like that?
I think a few, but I'm pretty sure I understand how this would work. If they're both going up, then they're direct. If one
No,
goes
that's
up,
the problem. No, that's what I used to think too. In other words, if this was my table, that is a direct relationship. K is 2. In other words, if y equals kx, and I plug in one set of points, I realize that k has to be 2. Okay?
mm-hmm.
But change one number like that in this table, and now when x is going up, y is still going up every single time, but this is not a direct relationship because y equals 2 times x only up to there. It no longer equals it after that point. So to answer those kind of problems, if they give you a table, choose one set of points, figure out what k is, and make sure that every other row follows that same rule.
Okay.
In other words, if you were looking at this table, you would plug in x is 1, y is 2. Therefore, if it's a direct relationship, every row has to follow that equation. And
Okay.
the fifth row does not.
So it not only has to go up, but it also has to...
Has to maintain
be
that
the
same k throughout.
Right.
And
Okay.
that's whether it's going up or down. In other words, it applies to inverse relationships also.
Okay. So this would be neither.
This would be neither, but if I replace that with a 0, then it's direct.
Right. What was the other thing? The fundamental theorem of variation. I can't remember if we talked about that.
I don't think we did. I'm going to have to look it up. Do you know what it is?
Not really. I never really understood this, and I don't think I have notes on it. We never really talked
Well,
too
that's
much
one of the
about it.
reasons I don't know what it is because I'm not used to dealing with it either. Very few people. It must be something fairly straightforward. Hold on, I'm looking in my algebra book for this particular direct and inverse and joint. Have you talked about joint variation?
A little bit, yeah. That was my next question, was joint and combined.
Okay. That's all joint does is combine direct and inverse.
Right, it's with more than one variable.
Right. Okay, let's see if mine has anything about that theorem. It does not. My Algebra 2 book does not talk about the theorem. Let me look it up in the index and see if it has any reference at all to it. No.
It may be on the internet. Let me check.
Okay. Yeah, actually I misspoke when I said joint was combining direct and inverse. It isn't necessarily. Joint is just having two variables.
Right, combined is combining them.
There you go. That combined must be direct and inverse at the same time.
Right. And really, those are just the same idea, just two different equations.
Yeah. Interestingly enough, my book, my Algebra 2 book, also does not talk about the graphs of any of them. In other words, it doesn't say that you can know that it's linear.
Right. Yeah, the graphs I think I'll be all right because we're allowed to use our calculator, so
Okay.
as long as you can plug it in.
Yeah. I do have a few table problems in this book that might be worth looking at. Determine whether x and y show direct variation, inverse variation, or neither. Do you want to try one or two of these?
Yeah, sure.
Okay. Let me find a good one. Yeah, this is pretty good. All right. So what would you say off the get-go?
Okay.
It's either direct or neither. I mean, it's either inverse or neither, right?
Right.
So you don't have to test the direct. So if we try to assume that it's inverse, then it has to fit this model right here. Do all of those points fit that model?
Wait, why couldn't it be direct?
Well, because y is going down as x is going
Oh, right.
up.
Yeah, sorry. Yeah.
So that's the first thing you look for, is whether,
Right.
what directions they're going.
Yeah. Let's see. So 1.5 equals 20. So how would you'd write it out? 20 equals 1.5.
No, 20
I mean,
equals k
equals
over
K
1.5.
Right.
So what's k equal?
K equals 20 times 1.5.
Okay. Now, every other row has to match that. In other words, does y equal 30 over x for this row?
So 30 divided by 2.5.
It's 12.
Yep. 12.
So yes. How about the next one?
30 divided by 4, I believe is that. Something
It is. Mm-hmm.
Okay. And then 30 divided by 5 is 6. So
Okay.
yeah.
So they all match, and they all have to match. If even one of them is off, then it's a neither.
Right. So this one's inverse.
This one is inverse. Let me find another one here. Okay. I'll try not to say anything here.
Okay.
Very hard for me.
Okay, so first thing is it's direct. I
Okay.
mean, it's the first thing we can kind of guess at. So 217 equals k times 31. That means that 217 divided by 31. 7. So k equals 7. Oh, 2. Yeah, 7. I believe. Okay, so now, let's see. So 7 times 20 needs to equal 140, which it does. 7 times 17 equals 119. And then 7 times 12 equals 84. So this one is direct.
Yeah. Unfortunately, when I'm trying to find one that isn't, but I can't do the math in my head.
Right.
So I'm just doing these in order. Let me see if I can figure out how to do the math in my head here. Well, here's an interesting. This isn't very hard, but I need to go any further?
No.
No, I think we can say neither as soon as it goes in two different directions.
Right.
Even though as x goes up, y goes up, and when x goes back down, y goes back down, but then when x goes back up, y goes down. So this is easy.
Right.
Easy in the sense that we don't have to do any arithmetic. We can immediately say that this is neither.
But if it did go back up, if they go up and down, but at the same points, is it still valid to be, or is that would still be neither, wouldn't it?
Yes. In other words, you're saying if it went like this,
Yeah.
where y is always twice x. Well, this is kind of interesting because they do all fit that model right there.
But it would be neither because when x goes up, or well, I guess actually that's kind of, wouldn't it be both? Oh, that would be combined, wouldn't it then?
No, no, this is neither. I don't think you're ever going to see this. They're never going to give you one like that.
Okay.
It's not combined because it's not direct combined with inverse. Notice direct, x goes up when y goes up. X goes down when y goes down. Inverse is the opposite. So if anything, this would be direct. And it would be direct if I listed everything in order. In other words, if I put the 4-8 in the middle and the 6-12 at the end, it would be a perfect direct relationship.
Right.
So that's why I don't think you're going to see this. They're not going to give you something that is that confusing. The one, let me see if I can't even find a good one here that goes the same direction the whole way. All of them go different directions. So the moment it goes.
That's all right. I understand that.
Okay. Yeah, here's a good one from my book. Tell me whether this is, tell whether x varies jointly with y and z or not.
If x equals, oh, jointly.
Tell whether x varies jointly with y and z.
Yes.
Yes, it does. Okay, it's got a number of them here. That one it did. About does x vary jointly with y and z?
I'm not really sure how to solve these or how to figure that out.
Well, let's get the z on the other side. In other words, if x varies jointly with y and z, it needs to be on the left side all by itself. So if I multiply both sides by z, I get, and yes, x does vary jointly with y and z.
Okay.
Okay. So when we solve for x, what do we get?
Y, or 4z,
Or 4z.
y, I guess.
4z divided by y.
Oh, right, yeah.
So x varies directly with z, but inversely with y.
Okay.
So this is not, x does not vary jointly with y and z. Since jointly means that it has to be x equals y times z times k for it to be a joint. In other words, it's only going to be joint if you can make it look like this. And I can't here. I got to divide by y.
Okay.
How about this one? Does x vary jointly with y and z?
Let's see. think, yeah.
It does, because I can write this x equals 1/2 yz, and they're being multiplied, and k is 1/2.
Okay.
All right. Let me give you a couple here where it says, tell whether x and y show direct variation, inverse variation, or neither.
Um, I guess that would be, that's kind of weird.
Solve for one variable. It doesn't matter which one.
Okay. So I guess there would be, will it be y, or 1/4 divided by y?
Yeah, you can look at it like that. Excuse me. So what kind of relationship is that?
That's inverse.
Yes. Okay.
That's direct.
Okay.
That's also direct.
That's neither.
Oh.
Remember the graph has to go through the origin? Well, this graph goes through
Oh, right, -3.
-3.
Okay.
Let's see if there's any good ones here.
Um, This would be inverse.
This would be neither. In other words, you want to solve for one of the variables. It doesn't really matter which one. So if I try solving for y, again I get this, which is the same.
Wouldn't it be divided by 2x, though? Oh, no, I guess it is minus.
No, we have to subtract 2x.
Right, yeah.
So this would basically be that same, got that y-intercept that's not 0.
Okay.
Okay.
Let's see, this one would be, that would be neither.
Solve for one variable.
Wait, okay. Right. Yeah, well, wouldn't it be neither?
Well, if I solve for y, I get 18 divided by x, which fits k over x inverse.
Inverse, yeah. Wait, what was I doing?
Just in order to determine what it is, solve for And it doesn't matter really which variable I solve for. If I want to solve for x, I get the same thing. I get 18 over y. So they still have an inverse relationship, no matter whether I solve for x or y. And that's why
I just did something funny there.
That's why this problem says, tell whether x and y show direct variation, inverse variation, or neither. It doesn't really specify whether you're defining it as y or x.
Okay.
How about this one?
That would be direct.
Okay. All right. Now, let me see if there's any other problems here that might look interesting. They're all very straightforward, except the ones like this. These are the only ones you got to be careful for. Is that direct, inverse, or neither?
That's neither.
Okay. How about
that's inverse.
it's neither?
No. Oh, yeah, that is neither.
In fact, you can almost say that if you see a plus or minus sign in the thing, it's neither.
Okay.
There's no way to handle a plus or minus sign. Not in every single one of these problems that had a plus or a minus sign in the equation was neither. So that's almost a clue. And of course, the most famous one of all is the force of gravity. So how would you describe this relationship? If M1 is the mass of one planet, M2 is the mass of another planet, and D is the distance between them, and G is a gravitational constant, meaning we know what it is. So you would say the force of gravity between two planets is what?
Force is equal to, well, it's equal to the gravity constant.
Well, it varies what?
It varies inversely.
Well, it varies jointly with the two masses and inversely with the square of the distance.
Okay.
So if I was describing this relationship, I would have to say all of that. I would have to say the force varies directly, or rather jointly, with the mass of one and the mass of the other, and inversely with the square of the distance between them.
Okay.
And this G is just another K. In other words, if I made that K, now you can see that it varies jointly with M1 and M2 and inversely with the square of D.
All right.
That was actually, Newton came up with that. Sir Isaac Newton. All right, I don't know what else. Let me just see. I've got 5 types of relationships here. Let's see if there's any that we haven't talked about. No, no, no. So describe this for me. Z varies what?
That's combined.
Well, so how you would say z varies directly with y.
Okay, yeah, z varies directly with y and inversely with x.
Yes. Okay. Well, I think we've beat this thing to death except for the theorem, which I don't have access to, so I'm not sure what that says. And the graphs, and I'm having a hard time imagining what the graphs are going to say. In other words, because sometimes the graphs are linear, sometimes they're parabolic shaped, sometimes they're cubic shaped. So I'm
Yeah.
not sure how one makes a general statement about the graph.
Okay. Yeah, we've been doing a lot of scatter plots.
Okay.
But yeah, just with the calculator.
And then finding the best fit, a linear regression.
Yeah, just an equation.
Well, but in other words, if I had a scatter plot that looked like this, and you told me that draw a linear straight line equation that best fits those points, it would probably look something like this. But the way you would get that is by going into your calculator and doing a linear regression. Okay, it wouldn't have to be linear. In other words, you could also think that maybe there's a dot over here and a dot over there. Now it doesn't look so linear, it looks more parabolic. In other words, if I thought that it had more of this shape, I would do a quadratic regression in my calculator. So whatever regression you define is what it's going to try to draw through that scatter plot. It's going to, if you do linear, it's going to try to draw a straight line. If you do quadratic, it's going to try to draw a parabolic, the best parabolic fit through those points. There's varying types of regression. There's logarithmic, there's so your calculator is going to have a number of choices to choose from. You know, if you're just looking at a bunch of dots, sometimes it's hard to tell whether it's going to be a linear regression or a quadratic regression that best fits those dots. In my original example, when I didn't have those two there, that looks pretty linear. In other words, I can draw a straight line, and there's not very many dots that are very far from that straight line.
Right.
But if I ask the calculator, do a quadratic regression through those same points, maybe it would come up with something like this. So, in other words, part of putting a line that is the best fit for a scatter plot is determining whether you want it linear, or maybe linear is the only one you've talked about at this point. It's possible that that's the case. So.
Okay. Yeah. I mean, we've just been doing it on the calculator, just kind of making our. I think it is just linear. Or well, the calculator draws the line for us.
Right, but you
from the way we've been doing it.
You still have to tell it whether you want a linear regression or not, because there's multiple types of regression. If you look on your calculator and you go to regression, you'll see linear, you'll see quadratic, you'll see exponential, you'll see logarithmic. At least those four I can think of.
Okay. Yeah. Well, I think we've only talked about linear then.
Right. Probably.
Yeah.
What else? Anything else you want to go over?
I think that's
What was on
just
here?
about it.
Let me open that chat window again. Just make sure graphs of these models and creating models for these data. Creating models for these data. That's pretty general. Let me see if I can think of something real quick here. Yeah. How does a person's age compare with their life expectancy? Their remaining life expectancy.
I guess it's inversely because the older you
Yeah,
get.
exactly.
Yeah.
So it would be K over that.
Okay.
So there would be a real-life model that follows an inverse relationship, just like the force of gravity is a model that follows both direct and inverse. Or joint, I guess I should say, because it's two variables that it's directly varying with. On your review material, do they not give you any problems, or it's all just subject matter like you put in the chat window?
No, they give us some problems.
Okay. Are there any kind of problems that we didn't go over? Though any kind that are different than the ones we've been going over?
Let me check here for a second. I don't think so. I mean,
okay, we
basically,
covered quite a bit of different type problems.
Yeah.
So
I mean, they all link back to the direct and inverse.
Yes.
Really. I mean,
yes.
There's just
Here, let me
big
just
paragraphs of questions.
caution you about one thing that I've seen students do. And that's memorize too much. In other words, if this is all you want to memorize right here, you don't want to memorize that y over x equals k and that k equals y times x. The reason, if you try to memorize all four of these things, it's real easy to get confused and get them switched. Because this looks very much like a direct relationship, but it's not. It's just the algebraic manipulation of this. So, in other words, you may have to do this. I gave you numerous problems where you had to divide by one of the variables to find out what kind of relationship it was, but don't memorize those. If you only memorize these two, you'll never make a mistake. For one thing, this looks like the direct. Direct is x goes up, y goes up, x goes down, y goes down, and this looks like inverse. So it's pretty easy to memorize it like this and not make a mistake.
Okay. Yeah. I mean, yeah, so when I was doing the worksheet, I just followed those two equations, and I got most of them right, so.
Okay.
It's really just being able to plug the information in.
Okay.
All right, yeah.
Sounds good. Well, good luck on your test tomorrow.
Okay, yeah, thank you.
You're welcome. Talk to you next time, Thomas.
All right, yeah.
Bye-bye.